Okay, so we started with the metric space. We started with a set and a function, distance function with some basic properties of distance. Then we made this X into a topological space. We defined open sets, and using that open sets, I mean, the collection of open sets satisfies the conditions for a topology, and it's a topological space. Then, I mean, of course, when you have a topology, you can define continuity and all that. So we define continuity, convergence, and all that. Okay. So, and then we proved that the continuous function, the collection of continuous function, separates points in the metric space. Okay. So we proved all that. So now we want to see, I mean, we want to study more properties of this metric, topological properties of this metric. Okay, I wanted to do it in the last class, we didn't have time. So let me just make it as a remark. I don't want to define all that. The first one is proposition. Okay, X is a metric, XD is a metric space. We always deal with metric space. Then one X is Hausdorff. I will write it in the bracket what it means. Okay, Hausdorff. Hausdorff as a topological space. What it means is for X and Y in X and X not equal to Y, there exists open U which has X, which contains X, and V which contains Y, and U intersection V is empty. This is clear, no? So, I mean, we already know that it separates points. I mean, continuous function separates that. You can take the, using the open set, you can do it, or you can just take R is equal to dxy by 2 or something. Then dxr intersection dyr is empty. These are open sets and it will follow. So this is clear. Just you want to remark it. Just want to record this. The second one is any metric space is normal as a topological space. Normal means for closed set, I mean, whatever singleton sets are actually closed set. So whatever is true for singleton set is true for any closed set. That's what we are going to prove. So for closed subsets, F1, F2 contained in X with F1 intersection F2 empty. If you have two disjoint closed set, then there exists open U comma V with U intersection V empty, and F1 is contained in U, F2 is contained in. So if you have two closed sets, then you can find open sets which contains those two closed sets. I mean, if you have two disjoint closed sets, then you find open set which contain those two closed sets respectively, and their intersection also empty. Okay? So proof of 2, we indeed prove the following. From this it will follow. There exists continuous function f from x to the interval 0, 1. This is a metric space as a subset of R, such that continuous, such that I mean, it takes the value 0 in precisely 0. I mean, it takes the value 0 precisely in F1 and 1 in F2. So F inverse of the singleton 0 is F1, and F inverse of singleton 1 is F2. Okay. We claim this, we'll prove this. Once the claim is true, claim is proved, take, of course, U equal to F inverse of 0 half and V equal to F inverse of half, open interval half 1. These are, of course, open in 0, 1 in that metric space 0, 1. These are open sets, and inverse image is continuous, inverse image is open, and this will satisfy this condition. This will be the U and V required, and that will be disjoint clearly. Okay, inverse image of disjoint Z is disjoint. in real line, but in this metric space, it is open. If you want, you can take it -1 if you wish, but you'll only, something is open here. If you have, we proved that if you have a subset of a metric space, then you can restrict that metric to that subset. And anything is open in that subspace, if and only if there exists a bigger open set with intersection, I mean, whose intersection will give this set. So if you take -1 this, then it will give 0 half. This is open in this set. If you take any open ball here from 0, 0 is the only problem. If you take any open ball here, it cannot go outside, it will be inside. So, so by definition, it's open. Okay, so we only have to prove the claim. So proof of the claim, take. So we have already proved that df1, I mean, for any set A, we can define a function dA. In the end of the last class, we proved a function df2, which are from x to r, 0 infinity actually, continuous. We have proved that they are continuous, and take f to be df1 by df1 plus df2. I mean, you remember this function, dA of x is equal to infimum of dAx. A in A for any set. We proved that this is a continuous function. And for this set f1 and f2, I take those functions. Okay? df1 by df1 plus df2. Okay? And we proved that df1 x is 0. There's some problem in the tongue. So df1 x is precisely 0. I mean, df1 x is 0 precisely when x is in f1. Okay? So because of that, for x in f1, this is 0. Of course, denominator is not 0. I mean, because it precisely happens in f1 only. And since it is disjoint, it will not happen in f2. Okay? So this is 0 in f1, precisely in f1. So this condition is satisfied. Okay? And when it is in f2, this is 0. df1, and this is not 0, so it will be 1. So clear. Okay? So those two conditions are satisfied. Okay. So what you were asking before the class, let's come to that. So there are many more things to talk about continuity. We'll come to that. I mean, when we discuss compactness and other things, we will discuss more about continuity. So we will use prove the following proposition, which you must have seen for real numbers or something. So everybody knows what is uniform convergence. Maybe I'll write definition. Fn is a sequence from x to y. xy are metric spaces. Then Fn converges to F uniformly. Functions conforms uniformly if given epsilon goes greater than 0, there exists the n such that d fnx fy fx less than epsilon for all n greater than n. It is just this n does not depend on x. That's all. Okay? This is true for all n and for all x. There's a single n which will satisfy this. Okay? When the set is infinite, if it exists for each n, it need not exist for the whole x, right? When you can have the increasing n and it will blow up. So it did not happen when the set x is infinite. Okay? So this is uniform convergence. Or you can take a supremum here and you can remove this condition and you can put a supremum here. Supremum over x is less than proposition. And functions. So I mean, I just want to write this uniform limit of continuous function is continuous. That's all. That is Fn x to y continuous and Fn converges to F uniformly. Okay. then we want to prove f is continuous. Okay. That's a uniform limit of continuous function is continuous. So we have a collection sequence of functions which converges to f uniformly, and we want to prove that f is also continuous. And you know the trick. It is just you have to be, I mean, you have to be careful where you are using. There is some little bit of subtlety which you have to know. So you are going to use the triangle inequality. You want to talk about the continuity of f. To talk about the continuity of f, given epsilon, you have to find a delta, right? So the delta you want to find it for this f of x, f of y. So given, I mean, you want to prove that you want to take dxy less than delta. You want to find a delta such that when delta set xy satisfies this condition, you want to prove that this is less than epsilon. So for that, I write the triangle inequality, then argue this is less than or equal to. You use the triangle inequality twice, and you get this f of x, fn x plus d of fn x, fn y, okay, plus d of fn y, f of y. Okay, we use the triangle inequality twice. So now to prove f is continuous, I have to get a delta such that dxy less than delta will imply this is less than epsilon. But I know all the fn's are continuous. Okay, so I can fix a n and choose a delta for this function. But then I have to make these two smaller than epsilon or epsilon by 3, whatever, doesn't matter. Huh? I have to make this smaller. Okay, but then you can make it uniformly smaller by choosing a n. So that is where the uniform limit is used, uniform convergence is used. Okay, by uniform convergence, I mean using uniform convergence, choose n such that f and d of, we always tend to write the modulus. Uniform limit of fn x, f of x, fn x, f of x or f of y, whatever, is less than epsilon for all n. I mean, it's true for x and y, okay, and d of fn y, f of y. Both are less than epsilon. Okay? Both are less than epsilon for all n greater than, for all n. Oh, for choose a n such that this happens. Just someone choose a n such that this happens, which is possible because of uniform continuity. Okay, after that also it's true, but this is enough. Okay? Now I replace this n by that n. Okay? And choose delta greater than 0 such that d of fn x, fn y by continuity is less than epsilon for all d of xy less than delta. So it will follow. Fn is, no, it's not about, it's continuous. I am not using that. I am only fixing a x and y. I mean, you are fixing a x. Okay. No, it's not about uniformly continuous. X is fixed here, and then for all, I mean, no, it is all that x is fixed here, and then dxy less than delta. That's all. I mean, x is fixed here. You want to prove the continuity at x. Okay, fix x. Okay? That is for all y. I mean, for all dxy, for all y, such that this happens. Okay, that's right. Anyway, you should go through this and convince yourself. Okay, and it is just that you have to choose a uniform. I mean, it's not about uniform continuity. The whole thing is not about uniform. It's only about continuity. Okay, so we are fixing a x and doing this. Okay, yeah, good point. Anyway, this line. Now, first I am choosing a n by uniform continuity, uniform n for both x and y. That's enough. Okay. I mean, x and y are arbitrary, of course. For a, y is arbitrary, x is fixed. It's also arbitrary. Okay, but arbitrary but fixed. Okay. So for x and y, I choose a n. Now this fn is continuous, no? At x, okay, at an arbitrary x. So for that, you can choose this delta. And when, so now when x and y are less than delta, this will be less than epsilon. This will be, this is both are already less than epsilon. The whole thing is less than 3 epsilon. It doesn't matter whether it is epsilon or 3 epsilon. Yeah, that's all. It's fine. So now we choose this is fine. I don't have to write all that. If you want, you write epsilon by 3 on that. That's not needed. Okay. Okay. So now you were asking about the closeness of. So now, so if you have any bounded function, I mean, if you have any, so okay, S is any set. Yeah. So now you. Yeah. So now we need a metric space. When we are talking about 0, 1, I mean, we didn't talk about C of X for any general metric space. We are talking about C0, 1, but it will work for compact metric space later. Okay, when we do compactness, we will define C of X and show that that's a Banach space. I mean, there is a norm and we will do that. So you want to talk about, you are asking why is C0, 1 contained in B of 0, 1. B of 0 means all bounded functional, it's closed. Okay. So what if to prove close, what you have to do? If you have something in this and F1 converges to F, okay, then F should be here. What is your confusion? F1 is contained here. They are continuous, and they converge in this norm. Supremum norm means they converge uniformly. That's same as that. Okay. So F should be here. So it is closed here. Why F is there? Because it's continuous. This is all continuous function. F1 converges to F uniformly, then F is continuous. Okay. So F is in C01. Yeah, that's all. So from this, it follows that this is continuous. And this is just a remark. There is really nothing to prove in this. Okay. So C01 contained in B01 is closed. Okay. So the next concept is again a topological concept, the definition. So we have a set, I mean, it's all happening in some metric space. So if you have a set S contained in, maybe we'll take a general X system. Okay. Otherwise, you have to restrict to a subset. Okay. So is said to be dense if S closure equal to S. Okay. If the closure is called, I mean, closure is, or you can talk about some set also. I mean, you can generally, if you have A not contained in A, for that A has to be closed or something. A is closed or something. If A not closure equal to A, then we say A not is dense in A. Okay. Okay. So this is equivalent to saying, by the definition, because we may use any of the definition, by definition, this is equivalent to saying there is a sequence in S such that, I mean, for all may be misleading. For any arbitrary X in X, there exists a sequence Xn in S such that Xn converges to X. Okay. This is the meaning of that. Right. This closure is that means anything in X is a limit point of that, and that means precisely that. Okay. Okay. Which is also equivalent to saying, I mean, this is supposed to be usually the definition of limit point or something. For all B XR with X in X and R greater than 0, there exists a X in, there exists a X naught in Y or whatever. Y in S such that Y is in XR. Okay. That is BXR intersection S is not equal to empty for all X in X and R in R greater than 0. So every open ball should intersect with that set. That's what it means by its dense. Okay. Okay. Now I give another assignment. which I'm supposed to, I will write it. Of course, I will give you the proof, but you have to argue it carefully. That's all. So if you S contained in X is dense, and F from S to Y is another metric space. Okay, X and Y are metric space, Y is another metric space, is uniformly continuous. Then it can be extended. Then there exists a F tilde. There exists a unique. You have to prove the uniqueness also. Unique F tilde from X to Y, continuous again, such that F tilde, when you restrict to S, is there. The question is clear, problem is clear. Any uniformly continuous can be extended from a dense set to a closure. That's all. Which is not true for a general continuous function. For example, you can take 1 by x or something. Counter example, 1 by x. This is also not true for a general continuous function. You can take x power n in 0, 1 or something. I mean, counter example for this. Counter example. Take x power n. The sequence x power n contained in C01. They don't converge uniformly, and the point-wise limit will not be continuous. Okay. So that implies that it doesn't point-wise limit will not be continuous. So it is actually not uniformly continuous. Okay. So, and here you can take the 1 by x on. This cannot be extended to the closure, for example. Okay. It's not uniformly continuous. Okay, these are a counter example. So okay, so yeah, you should, of course, how to do it is clear. I mean, this set is dense here, so everything there will be a, I mean, there will be a sequence here which will be converging to that, and you have to prove that that limit exists, and that limit does not. I mean, then you can define that to be the function. I mean, that limit means f of xn. That limit exists, and that does not depend on the sequence. I mean, the function is not that defined on that. So there may be two sequence may converge to here. You have to prove that that's well defined. Okay, so that limit does not depend on which sequence you take. So the function is well defined, and you have to prove further that that is actually continuous. Okay, so a little bit of work is involved in this. Okay, now another definition. A metric space XB is separable if there exists a countable dense subset. Then we call it separable if there is a countable dense subset. Okay. Example, of course, real line, you have rationals which are countable and they are dense, you know. And similarly, Rn, you can take rational tuple and that will follow. Similarly, you can have Cn, all that. There is no need to prove, you know, that rationals are countable and they are dense. The example is L1 is separable. L1 is all those sequences xn such that summation mod xn. You can take either complex number or real number. Okay. And the norm is precisely this is a norm. Norm of the sequence is this. We've defined this metric space. Okay. This is a norm linear space. This norm linear space gives us a metric space in the M. Okay. Fine. This L1 is separable. I'm going to prove. I mean, I'm only announcing it. So proof. Before the proof, maybe this, note this. Note. S1 contained in S. There is some problem in this dense definition. I mean, when I say this, then it should be a closed set or something. Something need not be a closed set if something is dense. So you take this definition of this. I mean, this definition does not involve this. So I'm slightly, there is some problem. If it is a closed set, then it is true. If something need not be a closed set to say something is dense. Okay? So by density, I mean that for any xn. So it is only this way. Okay, this doesn't imply that. I mean, what I mean is, if we have a set S which need not be closed, I say S1 is dense in S, okay, meaning there exists a sequence in Xn. There's a sequence Xn such that Xn converges to X for all X in S. Okay, if you take any X in S, then there is a sequence here which converges to that. Or you take any open ball with center here in X that will intersect with this. Okay, so this is what I mean by S1 is dense in S. I mean, the closure need not be here. Closure may be bigger. Now I defined here as for a general metric space, S contained in X is dense means its closure is this. Okay, this is okay. This definition is okay, but this is very particular for a closed set. Okay, yes, this set need not be closed. I am saying here, this S may not be closed, but still you can talk about density. S1 is dense here. If you can, for any X here, any element here, you can find a sequence converging to that element. Right? Or you take any open ball with center here and some radius, any radius, that should intersect with this. Both are equal in definition. Those two are equal in definition. Okay. So that is density. Okay. So take this as the definition. Anyway, you will, I mean, if you read a book, you will find it. I mean. Okay. So the what I want to note is, yeah. Closure with respect to, that's also fine. Yeah, that's also good. Closure with respect to X. Yeah. Yeah, but then we have to go through something. No? Let's not, I mean, it's closed here. And, I mean, let's take this as a definition. There won't be any confusion. Then you have to prove that something closed here is closed there, and that is true only for a closed set, and all those problems will be there. Let's not go through that. Take this as a definition. I have written two equivalent definitions to take the next two definitions. Okay. Okay. So if S1 is dense in S and S is dense in some X, okay, is dense. You usually write like this, the subset, and then write it on the top, dense. Then S1 is dense in X. Okay. If some S is dense in S1, S1 is dense in X, then S1 is dense in X. That is clear. Okay. Is an exercise. For example, if you take an open ball in X, okay, any open ball in X, that will intersect with S. Okay. Then you can find, but any element, for any element in that open ball will intersect with S. So you can prove that the original thing will intersect. A little bit of work. Okay. So you can verify. This is an exercise. Okay. So we use this to prove this. L1 is separable. So let script F be the, I mean, we are working inside L1, all summable sequences, absolutely summable sequences. Let script run be the all Xn and equal to all sequences such that Xn is non-zero, is not equal to 0, only for finitely many. That is, after some time, it will be 0. Okay? After some n, it is 0, finitely many. So, claim is one is dense. Is this clear? So, what do you have to do? Given any element here, you have to find a sequence here. Okay? Let X bar be a sequence L1. For that, I have to produce a sequence. Of course, this is a space of sequence. So I have to find a sequence of sequences. Okay. Right. Okay. Now take yn bar. This is a sequence of sequence. Yn bar equal to yn bar. I mean, yn bar at k equal to xk for k less than or equal to n, equal to 0 for k greater than. Is okay? Definition makes sense? I am just taking a sequence here, just truncating at n, after that it is 0. That forms a new sequence in this subspace. Okay. Then I have to prove that that converges to that. So for that, to prove that, I mean, I'm just going through it because what you have to do, it should be clear what we have to do. Now you take the norm of this x bar. See, I have taken a x bar in this L1. Okay, x bar in this L1. Then I have produced a sequence here. That sequence converges to that. That's what I have to prove. So the norm between them should go to 0 as n goes to infinity. The distance between them. So x bar minus that yn bar, norm 1. Okay. This is equal to summation n equal to 1 to infinity x bar at n, okay, minus y bar n, maybe k here at k, y bar n at k, mod of this. Okay, but they are same for first up to n, so they will be 0. So this is equal to summation k equal to n to infinity mod of x k, k equal to n to infinity mod of x k, k equal to 1 n to infinity. This goes to 0 because it's square sum. This is because it's absolutely summable, right? Because it's in L1, by definition this goes to 0. Okay. So this y bar n converges to that x bar in L1 in this matrix. Okay. So this implies f contained in L1 is dense. Now take f q or something contained in f sequence with rational entries. Okay. This is finitely many n with rational entries, which is countable. I mean, finite. It is just finite product of rationals are. I mean, countable set is countable. I mean, infinite product is not countable. Countable product is countable. Then you take the union of all those things. I mean, okay, let me take fqn, okay, which is all those things up to x1 up to xn and 0, 0, 0, 0, 0. Okay, goes like this, and xi is in. This is clearly countable. Okay, and define fqn equal to union of fq equal to fqn. Okay, union of countable set is countable, so this is countable. Okay, and now this is dense there. Is dense. I'm just giving one example where you have to prove it like this. Okay, these are all the steps involved. So fq in f is dense and f is dense in L1. So this is a countable set which is dense in L1. Okay. So dense. So L1 is separable. Okay. If you have any doubt or if you want me to go through the argument, repeat what you tell me. I mean, what is happening? You want to prove L1 is separable, right? To prove L1 is separable, what you have to do? You have to produce a countable dense subset. Okay, countable dense subset comes later. First, I am claiming that some f, which is defined like this, is dense here, right? So this is dense here. To prove that, what you have to do? You have to produce a sequence here which converges to any element here. I take an arbitrary element here. I have to produce a sequence. I take this sequence and cut it in nth place. After that, it is 0. Truncate it at nth place. Okay, that's a new sequence. cutting at n is a new sequence, and if you collect that sequence, you collect those sequence, that's a sequence of sequence, right? That sequence converge in L1, which is rigorously proved here. You just compute the difference. That is nothing. It follows by definition. That converges to 0, right? Because this minus this one norm is just the summation of the mod of the difference. Well, first n places it is 0. It is same. So the difference is 0. After that, the another sequence is 0. That is the excellent one. So you get this. So this is a summation for k equal to n to infinity. The definition of absolute convergence is this goes to 0. What do you mean by something kind of series convergent? Positive. That is this going to 0. That's what the definition of the series absolute convergence sequence. The sum is less than infinity means it's precisely this. So it goes. So that is then here. And after that, it's all just you take rationals and do this. That's all. So you can argue the same thing for L2. Okay? For L2 also, square summable sequence. But L infinity, you cannot argue like this. L infinitely, this whatever the f I have written, finitely, that is contained in all L1, L2, LP. LP will be defined later. In L infinity, everything. But for L infinity, that is not dense. I'll tell you. That f is contained in L infinity, of course. That is just finitely, it's written, no? Only for finitely many n, it's not equal to 0. So that is contained in L infinity. And L infinity, that is not dense. L infinity is not separable, yeah. That's what I want to say. That's because, I mean, if it is dense, then it will follow. But it is not dense. I mean, that we don't need that statement to prove it's not separable. So this is a counter example. Okay? Counter example, L infinity is not separable. So, I mean, we cannot prove the same way because that is not dense. That f, the script f is not dense in L infinity. Because if you take finitely many of them, if you take the difference here, you get the sum here. But there, this will not go to 0. Because L infinity, the norm is norm of, you take any sequence, the L infinity norm is supremum of mod xn, right? That supremum can be L infinity is not separable. Yeah. That supremum norm will be a number. I mean, which will be bounded. That's all. It need not go to 0. Whatever there it has to go to 0 because it's summable. Here it will not go to 0, so f is not dense there. Okay? So because of that, it will not follow. I mean, it actually doesn't follow because of that, but that's not a proof. It just says this proof doesn't work. Okay, we have to prove this. We have to give a. I mean, we have to argue it. It's not separable. So we have to prove that there is no countable dense subset of L infinity. Okay, so to prove that, I will prove that there are uncountably many points which are separated by a fixed distance, by distance 1 or something. Okay? So let A equal to all those sequences xn such that xn is in either 0 or 1. You know this set is uncountable. You have seen this. You have seen this, no? Should I argue it? You must have, when you studied countable, uncountable, this is one of the set which is not countable. Or even for power set, you will do the same argument. Okay? It is just you take a sequence, I mean a sequence like this. Suppose if it is countable, then you will have the diagonal one. If it is either 0, I mean, you change. Okay, you know the argument. Okay, so I will not go through this. Okay, so this is an uncountable set. Okay. Okay. But then distance between any two element here, if you have an xn and yn in A, then the distance between them is now norm of xn minus norm of yn. Infinity norm is going to be supremum of mod xn minus yn. It's going to be either 1 or 0, but it has to differ. That is why if xn not equal to yn. Okay. They are not equal to means they have to differ at some point, right? So if they differ at point, there will be 1 and somewhere it's 0, so it has to be 1. Okay. So each element in this set are at a distance 1 from each other. Okay. So suppose L infinity is separable. That is, suppose S contained in L infinity, and maybe I put it down, I don't know, and S is countable, which is not possible. That's what I might say. Okay, suppose S contained is dense, let's say. S contained in is dense. Suppose S contained in L infinity is dense. Okay, then B of any xn with the radius half, okay, should contain an element from S, right? Contains a S in S, right? But there are uncountably many such xn, and B of xn half does not intersect with B of yn half. Okay, right? Okay. So S should be uncountable. Right? B of xn half and B of yn half does not intersect. So corresponding to each sequence S, you have a section if you want. Okay. And this collection is uncountable. Yeah. Okay. So this implies this collection S is uncountable. This is uncountable, so S is uncountable. I have not written each and every line. I overly said it. Okay. Clear? This set is uncountable. Not just that, they have a fixed distance of 1 between them. So if you take a open ball of radius half of each element here, that will not intersect the open ball of half with the other one. So in all those open balls, you will be able to find a S from this set because it is dense. And they are different because they lie in different open balls. So it should be uncountable. Okay, so that's why L infinity is uncountable. Sorry, L infinity is not separable. Okay. I think I will prove through a general statement about separability. So there is something called a base for a topology. If you have a collection of open set, definition, this is generally for a open ball. I mean, you can take the collection of open sets for a metric space. A base is something topological space. Okay. I mean, this is general for a topological space, but we will deal only with metric space. Okay. A B contained in the topological space is a base if every U open set in this topology is this way. Every openness in the topology is a union of sets in B. Sets in B. This is exercise, very easy exercise. This is equivalent to saying for all U in tau and X in U, there exists a B, depending on X, of course, in B, such that X is in Bx. It's like precisely like open ball kind of representation. Bx and Bx is contained in U. Just go through this exercise. Is equal. I'm saying something is a base if any element here is a union of this, union of sets here, which is equivalent to saying if you have any open set, I mean, by definition, your topology means you declare something as open set satisfying. Okay, so if you have any open set, then from the base you should for any x, you should be able to find a bx with x containing that. It depends on x. That's why I've written bx. Okay, so you get a set here. And that bx should be completely contained in U. You just write this definition, this implies this, this implies this. It's very easy. Okay? Please do that. Okay? So from this example, you get examples. All open balls are forms a base for a open sets in metric space, because any open set can be written as union of open balls. You take open balls which are contained in that and then take the union. Okay, but you don't need all open balls. You can take Bx 1 by n. That's enough. Okay. Oops. So you just take open balls with x in x and n in n, because every open ball you can find a smaller open ball. Okay, so this is a base for open sets in base for open sets in metric spaces. Okay. And a topological space is usually called as first countable if there is a countable base around each point. It's second countable if there is a countable base for the topology itself. Okay. Huh? Another example. Bx with rationals, if you want. Another, there are not too many. You need to cover the whole thing, no? Or if you have a dense subset, then B, you can replace this by a dense subset. X need not come from everywhere. That's what you are going to use now. That's what the statement I'm going to make. Okay. Proposition. I mean, if you these bases are very important if you use topologies which doesn't arise from metric. Okay. So you will work with this base and other things. Okay. I will give you an example later if you want on using non-linear space or something. Okay. There is something called weak topology that's not given by a metric space. There you can write down all these things. If you are interested, you will see later. Okay. So what do you want to prove? So I have to define more things. So definition, a topological space is general for a topological space. I don't want to say that. I don't need to define. I mean, I just said first countable, second countable. We don't need all. I will directly write the statement. So base countability. So maybe just a proposition. So XD is a metric space, and the following statement. This is the following statements are equivalent. Okay, when I write like this, that's what it means. One, there exists a countable base for the metric space. XD metric for XD. For open sets in XD, I don't want to write for XD. Okay, with the metric space for XD. There exists a countable base for that. Two, I forgot what I forgot to define is the following. I will define here, which you must be knowing already. I don't know. So if you have a subset A contained in X, okay, then U alpha in some set I, and U alpha contained in X open, okay, is an open cover. Of course, if it covers cover for A, if A is contained in union of U alpha in I. That's all. You have a collection of open sets. When you take the union, you should cover that. That's what is called open cover. Okay, if the collection is open, it's cover if it is just some set. If it is all open, then it's called an open cover. Okay, and if you take I naught is contained in I, okay, then a collection, then U alpha contained in I naught You just take a sub collection. Okay, this is what is called as subcover. Okay, that's all. Open cover, subcover. Subcover means you take this just a sub collection of that. Okay. So I mean and such that A is contained in U alpha, union of alpha in I naught itself. Okay. I mean the subcover, the sub collection itself covers this. You don't need the big cover. The sub collection itself is enough. That is what is called a subcover. Okay. That's a cover. This is a subcover. Okay. So if something has a countable base for that, then every open cover has a countable subcover. Means the sub collection is countable. That's what it means. Okay? Countable subcover. Subcover means you take this sub collection, okay? And the sub collection, I mean, you can take subset or something, but it's a collection of sets. We call it a collection of something. Okay? So so that collection, sub collection is countable. Then we call it countable subcover. So every open cover has a countable subcover. This is equivalent to this. Okay. And the third statement is X is separable. Every open cover for X itself. Okay. For X has a countable subcover. Okay. X is separable. Okay. So the proposition is clear. Okay. So we assume there is a countable base for this. That is, there is a countable collection of open sets, whatever. Okay. That the countable collection of open sets which generate all open sets. Any open set can be written as union of those sets. Number one. Then we want to prove that every open, assuming that we want to prove that every open cover is a countable set. Then assuming this, we want to prove that everything is separable, and then from 3 to 1, we want to prove. So 1 to 2, we want to prove. So we are assuming there is a countable base for that. Okay. So let B naught be a countable base. Let's write it UN, N in N. It's a countable base. Okay. Then we want to prove every open cover has a countable subcover. Okay. So let I write it Bn. Sorry, I changed to Bn because I want to use UN for something. Okay. Change to Bn. Okay. Let X is equal to, I mean, here because X is the whole metric space, I'm not using subset, I'm taking equal to. X is equal to union of U alpha in I. Now I have to prove that this has a countable subcover. I have to produce a countable sub collection of this which covers the X. That's what I have to prove. Okay. I write there. Okay. So how do you do that? I have defined B as that, no? I don't know why I put a B naught. There is no need for this. B. This is script B. Script B. I call B naught as this. B naught as this. All B in the script B such that B is contained in U alpha for some alpha. Okay. This B naught is also countable because B naught is contained in B. So this is countable. I take these things. Okay. Then of course it's clear that union of B in B naught, this B naught, B is also equal to X. Because B is a base, you will have, I will not write the argument for this, okay? I will say it. Because B is a base, if you have any open U, you will have these containing in that covering, I mean, whose union is that, right? So all those B containing in that which covers this U alpha are contained here. When you take the whole union, that should give the U alpha. So this is equal to, I mean, because this is equal to U of U alpha alpha n. This is equal to that. Because of that, okay, maybe I will write it this way. Then let's see. This is the argument. Is equal to union of U alpha. This is union, this is U alpha in I. This is equal to X. Okay. But this is a countable collection. Okay. Now choose U beta. Maybe let me write B. Okay. BK. Now choose UK such that BK is contained in UK. Such that some UK. Choose a UK. Okay. Now union of BK, UK is contained in UK, so union of BK should be contained in UK. So it's K, right? Now this is equal to union of this UK. K. I just write K equal to 1 to n, okay? 1 to infinity. K countable, okay? Countably many K. Okay? I mean, I have to introduce index set otherwise, okay? So you be careful when you write, okay? Countably many K, countably many. All the, I choose, you know, I have a unique BKs. I mean, BKs are coming from such that so that BK is in B naught. I'm just writing it, enumerating it, that's all. It's countable. I'm just enumerating this B naught as BKs, okay? So that BK is countable, okay? Maybe it's not needed. I write it like this, BK, so that K, this is countable, okay? BK is countable. Then I have to change the indexing set, that's all. I mean, I have to index this BK and B naught, that's all. Exactly, all those things. And I'm taking this BK. These BKs will give that. Okay, now I am corresponding with that BK, I choose a UK. Okay, now this UKs will cover all this union BK. Union of BK is equal to BK, and that is equal to that. Okay, fine. So we got a countable subcover. Okay. This is direct. Okay, it's just writing it is problem. Even I haven't written it precisely. I hope it's clear. Okay, but I have said it precisely, so you write it yourself. Okay. So now we have proved 1 implies 2, 2 implies 3 we have to produce. It's all trivial things actually, it is only writing it matters. So 2 is every countable, every open cover has a countable subcover. Then you want to prove that it is separable. So you have to produce a countable dense subset. Okay. Okay. So notice that Bx 1 by n is fixed. Yeah, n is fixed. Yeah. N is fixed, Bx in 1 by n, and x is in x. Is that cover? Is an open cover. For x, right? For every, you take every x and it's an open cover for x. Okay? Everything, it contains all x in x, so it's open cover. So there is a finite subcover. So B of x. So this n is fixed. So it varies with the m. X n comma m. Okay. X n comma m 1 by n, where m is a natural number. It need not be, I mean, it can be finite even. Okay, it doesn't matter. Point is. So I will not write it. You are just having a countable subcover. That subcover may be even finite also. So I should not write n or something. Okay. So this m varies over f. M is in I countable. See, that's what it means. Okay. Okay. This is a subcover for x. Okay. By because we have assumed 2, this is possible. Okay. Now the claim is, and this is true for all m and n. This x m comma n, m and n. So m is in I, which is a countable set, and n is in n, is dense. This is the claim. That's what we want to prove. It's a countable subset, and this is okay. So this is what we want to prove. So why is this true? So to prove that this is dense, we have to prove that B of x m comma n so we have to prove that we take take x in x, okay, and for any b x 1 by n, we have to intersect with this set, right? So call it S. Okay. We need to prove. So for take x in this, we need to prove to b of x m n, sorry, b of x 1 by n intersection S is not equal to empty. That's what we have to prove. Correct? Just think about it. This is what we have to prove. Right? To prove density. To prove density, you take any open ball, but it's enough to take open ball with 1 by n. Okay? If you have some bxr, then you can take a 1 by n less than that r and work with that. Okay? So we have to prove that b of x 1 by n intersect with S is this. So we have to produce a x n m corresponding to this, which is contained in this ball. Okay. How do we do that? Okay, what do we have? Is a that's a countable subcover. Okay. So, but x is, I mean, this is a countable subcover, we have noticed. Okay. So x is in B of, it follows immediately. X n m n comma m 1 by n, right? 1 by n for some m and n. Right? Now x is here, means x and m is, I mean, distance between x and m is less than 1 by n. This implies x and m is in B of x 1 by n, right? That's what we want to prove. This implies this, right? Distance between this and this is less than 1 by n. Distance between this and this, both are true, right? So this is what we want to prove. It follows immediately. There's nothing. Just the meaning is our same. Now 3 implies 1, which is also very easy. So now x is separable. So that x is a countable subset, countable dense subset. Then we want to prove that. We want to prove, okay. So let xn, maybe S is a countable, S contained in X is countable dense. Okay. Then B of x comma 1 by n, you can take rational numbers if you want, with x is in S and r in Q, is dense. No, is the claim. This is the claim. Sorry, claim is a countable base. Shall I do it, or is it clear to you? Do it as an exercise. I will say it orally and you will do it. Check it. We have, this is a countable dense subset. That's our assumption 3, because it's separable. Okay. Now we want to prove that. I will say it orally. Okay, finding it. So, so this is a countable base for that. What does it mean? given any open set U, you have to and a X. Okay, let me write. Let U contained in X be open and X is in U. Then you have to find a BXR. We have to find a BXR for this XR, which is contained in U. Okay, with this X, you will find, if you have a X, you will have the BXR contained in U. Now that BXR will contain something from S because it is dense, right? Because S is dense, what do you have to prove? You have to prove a countable base. You want to prove that this is countable. Okay, maybe Y, I take Y because Y and X may be continuous. You take a Y in U. Because U is open, BYR is contained in this. Okay. Now this BYR, which is an open ball, because it's dense, it has to intersect with this S. You will find something there. Okay. Take that element and then maybe R by 2 or something. That element with radius R by 2 will be completely contained in this BXR. You can prove, okay, by triangle inequality. There's nothing else. Okay, by triangle inequality. Because that is completely contained in that open ball, it will be contained in this. So that's what we want to prove for countable base. Just go through the definition, you will prove it. Okay. So rest is exercise, which I orally said. Okay. Yeah. Hey, so say it again. One by n is fine. No problem. Just okay. Okay. So let me define compact. What is a compact set? So what is compact set? Compact set is a generalization of some sort of, not finite set, some sort of finiteness. For example, you have this AB interval, closed interval AB. Okay. We want to generalize this in a metric space. Okay. So what are the properties of this interval? One thing is infimum exists in this interval, supremum exists in this interval. Okay. And if you any continuous function on this is bounded, or you know Bolzano-Weierstrass theorem, have you seen the proof of it? Bolzano, every sequence has a every bounded sequence has a convergent subsequence. Every sequence in this interval has a convergent subsequence. You have seen a proof of it. I don't know how to prove it. Okay, good. So these are all some properties of this set AB, closed interval AB, closed and bounded interval AB. Okay. So we can define a metric compactness using, I mean, you want to generalize this, but that will not be possible in infinite dimension, I mean, in general metric space. See, the point is, this is closed and bounded. But if you have some Euclidean metric space, like Rn or something, there all closed bounded metric space will, I mean, you see, if you define compactness by some property, like every sequence has a convergent subsequence, then that will not work in topological space. There you have to do something. You have to take nets or something. So that will work in metric spaces. Okay. If you use closed and boundedness, that will work in Rn or in finite dimensional vector spaces. That will work in finite dimensional vector spaces. So we need to use a new definition, and that definition is using this open cover subcover. Okay. But it is basically, the idea is you want to generalize this finiteness. How do you generalize this? Okay. After working for some time, someone came with this idea. So the idea is the following definition. We say it for a subset. K contained in X is compact. It is compact if every open cover has a finite subcover. We have seen that for separability, countable subcover, instead of countable, it should be finite subcover. If every open cover U alpha of K has a finite subcover. Okay. So if a metric space is the immediate corollary from the definition itself, or to the earlier proposition, immediate corollary, a metric space is compact implies X is separable. Right? We have immediately proved. Because if it has a countable subcover, it is separable. We have a finite subcover, so it should be separable. Okay. So we got this immediately. Okay, so I thought I can do more, but 6:15. Shall I go for 5, 10 minutes or? Okay, I'll stop.